Hello everyone. As you know from kinematics of rigid bodies, one way to perform kinematics analysis on rigid bodies is using the general velocity formula, which we call relative velocity formula. So basically, if you have an arbitrary rigid body, and you have 2 points on it, A and B, and this rigid body has an angular velocity of omega with respect to an inertial frame x, y, and z, then you can define the vector that connects point A to point B, and you call this R of B with respect to A, okay? And then you can say that V of B equals V of A plus omega of the rigid body cross R of B with respect to A, okay? So this is called the relative velocity formula. And if you know, it means that if you know velocity of one point, how the rigid body is rotating with respect to time, and the position of the 2 points with respect to each other, then you can find what? You can find velocity of another point, or sometimes the velocity of the 2 points are given, the positions are given, you need to find omega or some other variable. It's typically one or two components out of this set that is missing, or if it's in space, it could be even 3 components. But this is the way to find velocity of point of interest on the rigid body if you know velocity of one other point, the rotational velocity, and the position of the 2 points with respect to each other, right? Now, another way to analyze the problem is to use what we call instantaneous centers of rotation. And in that method, we are not going to be dealing with vectors, we are going to be dealing with scalars, okay? And I know some of you would prefer to deal with scalars than vectors and decomposing everything along I, j, and k. So maybe you find this method more convenient. So the idea for instantaneous center is this. If basically one point on the rigid body in this formula has 0 instantaneous velocity. So for a moment being, assume that this point A that I'm using to find velocity of B, this point A has instantaneously 0 velocity. So temporarily, this point, it doesn't need to be all the time stationary. Just at that moment, assume this guy is what? 0. Okay? So temporarily, again, it means like this point is what? Clamped down. You're rotating about what? Pure rotation about the point, right? Because if you look at here, then velocity of B is going to be omega cross R of B with respect to A. And you know that from here, magnitude of velocity of B, it is going to be omega times R of B with respect to A, or you might just call it R. And this is assuming that you are doing a planar motion. So here, this idea that I'm talking about is about planar motion, plane motions. So let me add that here for you so you know what we are talking about. So it's planar motion, which means omega is perpendicular to the vector R. Okay, omega is out of the plane and R is in the plane, whatever plane it is. Then angle between them is 90 degrees, so sine of the angle between, which you use for the magnitude of the cross product, is going to be 1. So magnitude VB is going to be omega times R, where R is basically this R here, right? This position vector between them. And the direction of that is going to be what? Perpendicular to both R and omega. So basically what you have is, if you draw that again, and this is point A and this is point B, so temporarily it means like A is like acting like a pivot. If you draw a position vector from A to B and call it R, and this is the rotation omega of the rigid body, then point B is going to move in a direction that is perpendicular to omega. Since omega is out of the plane, VB is going to be in the plane and it's perpendicular to R, so V of B is going to be like that. Okay, perpendicular to R, perpendicular to omega. And magnitude of it is clearly what? It is going to be omega times R, right? So all I need now is to use the scalars, correct? Right? Because all I need is to know the magnitude of R, the magnitude of omega, to find magnitude of VB, and for direction of that, I say it's perpendicular to the direction of R, and this which way, if you know the line of action perpendicular to R, which way, that is determined by omega, correct? If omega here is backwards, clockwise, then VB is going to be downward and to the right instead of upward to the left. So here, you see, I'm dealing pure with scalars. There is no vector, there is no cross product and anything. So this point A that at this moment has zero velocity, I call this what? I call this instantaneous center of rotation. Now, again, why instantaneous? Because I do not really need to have point A to be permanently fixed or permanent center of rotation. Point A in general could be moving. So the way that I'm putting this symbol and making it look like a pivot, just for better understanding, you do not need to have pure rotation. And you might say, well, could you give me an example where the object does not do pure rotation, yet it has a center of rotation? It has an instantaneous center of rotation, which means a point with zero velocity. Yes. So for that, I'm going to show you a rolling disk. So if you have a rolling disk like this, correct? And this guy is doing what? This guy is doing rolling without slipping. Okay, so no slipping here. Then if this point is point C and this contact point is point A, and the radius is R, and this object is doing rotation omega, it's very easy to show that V of A, based on what you learn in dynamics, that V of A is going to be 0, right? And for that, all you need is to use the formula, say it's equal to V of C plus omega of the rigid body cross R of A with respect to C, correct? And here I'm going to use a traditional XYZ. So X, Y, and Z out of the plane toward U. Clearly, you know, if the object is doing rolling without slipping, the velocity of the center, right, it is in magnitude going to be R times omega. That's the condition for rolling without slipping. So this is going to be basically R omega magnitude. It is moving toward right, so it is going to be R omega I. And omega is clearly has magnitude omega. The direction of it is clockwise, so it is going to be negative omega k. And R of A with respect to C is this vector. That's this vector. which has magnitude r in the negative j direction. And you know, if you carry the cross product, k cross j is what? Negative I. The two negatives would cancel. So you're going to get r omega I minus r omega I, which is 0. And it was completely predicted because you should not have any slipping. So it means the contact point should not move at that point. So the velocity of the contact point is temporarily what? 0. Okay, although it's not going to be all the time 0, this point will move, but at this moment where this guy comes into contact with the surface, it has to be what? 0 velocity. So the instantaneous center for a rolling object on a surface is what? Always the contact point. Okay, so we also show instantaneous centers with IC. So if you see IC means what? Instantaneous center of rotation. There is no permanent center of rotation here. There is only instantaneous. Where else that you can see that? Well, of course, if I have a rigid body like a pendulum, correct? If I have a pendulum, where is the instantaneous center of rotation? Well, of course, it's here, because not only this is instantaneous center of rotation, it is also what? It is permanent center of rotation. Okay, so permanent centers of rotation are, of course, also instantaneous center of rotation, right? But not every object is doing pure rotation. Sometimes objects have what? Translation and rotation, like this rolling disc. And clearly, there is always a method to find the location of the instantaneous center for those objects. And I'll show you how to find them and how to use them to solve kinematics problems for rigid bodies in planar motion. But that's the whole idea. Now, not always the instantaneous center for a rigid body is on the rigid body. Sometimes the instantaneous center might fall outside the rigid body, okay? And I'll show you that. Like when, where, could you tell me something like that? Well, if you have a wall and you have an object that is sliding on the wall like this. So if you put something like a ladder, any object at angle on the wall, and there is no friction to keep them in place, you know what happens, right? This point is going to slide down, and this point is going to slide to the right until it completely falls and become horizontal. Now, where is the center of rotation for this object? I'll show you in a minute that the instantaneous center for this object is actually here. Why, how, I'll show you, but there is no point on this whole rigid body that has 0 velocity at this point. If there is such a point, it has to be outside the rigid body. But, well, if it's outside the rigid body, why do you call it instantaneous center for that rigid body? This is where we use this terminology. We say the instantaneous center is on the hypothetical extension of the rigid body. Which means basically if you could make your rigid body a little bit bigger, like make it something like this, make it a rectangular object, right? Instead of that, you made it something like this. Now you could say your point temporarily is what? Is rotating about that pivot point just at this moment. Okay, so not always your instantaneous center is on the physical rigid body. Sometimes you have to extend it hypothetically to make the instantaneous center fall on that hypothetical extension. Okay, or for example, if you have an object that is doing pure translation, correct? So let's say you have a box here, and this box is doing pure translation. Where's the instantaneous center? Because this guy clearly does not rotate at all, and velocity of all points are the same, and none of them is equal to 0. So where is the instantaneous center? So again, we'll talk about it, but the location of that is at infinity. So it's perpendicular to this direction of motion, but it is where? It is at infinity. So you say IC here is at infinity. Because you can say a translation is similar to what? A rotation but the radius of this rotation is infinite. So if I have the velocity of this point, it is moving with velocity v, whatever it is. Okay, so let's say I know the velocity of this point v. And the rotation of this object is omega around the center. How much is omega? Clearly, magnitude v equals what? R times omega, as you know, right? And how much is omega? Omega is going to be what? V divided by R. But since this R is going to what? Infinity, and this V has a constant magnitude, then omega in limit is going to go to what? To 0, which means your object is not really rotating, it is doing a pure translation. So translation can be regarded as rotation about a center at infinity, correct? And that's where we say instantaneous center is at infinity. So these are different scenarios that can happen about the instantaneous center. If the object is in pure translation, instantaneous is at infinity. Sometimes it is outside the rigid body. Sometimes the object has permanent center of rotation, which is also the instantaneous center. Sometimes it is going to fall on the physical part of the rigid body. Okay. Anyways, this idea of instantaneous center is there is one point for the rigid body that I can assume the velocity of it at this point equals what? 0. There is a point called instantaneous center of rotation for which the instantaneous velocity is equal to what? 0. If that's the case, then velocity of any other point on the rigid body can be calculated by multiplying. So if I have this rigid body and this is the instantaneous center, if I want to know velocity of any point like P, all I need is the distance from that point to the instantaneous center. So we can call it R of P. And then what? Omega of the rigid body. And that means velocity of P is going to be equal to what? Rp times omega. And the direction of it is perpendicular. The line of action of it is perpendicular to Rp. Direction of it is determined by omega. Okay, that's the whole idea of instantaneous center, to avoid what? Dealing with the vectors and doing cross products. Now, let me show you how we can use this idea and solve a kinematics analysis problem for rigid bodies. So I want to go back to this rolling disk, okay, without the slipping, and then I come back to more complicated problems. So again, here, let's assume that we have a disk that is doing rolling without what? Without slipping. And I want to find, let's say, velocity of this top point, which I would call point B, let's say. Okay, so here there is this top point B, there is center C, and there is the point of contact A. The radius is r, and the angular velocity is omega. So if I ask you what is velocity of B, what would you say? Well, again, here there are two ways to approach it. Either you use the idea of instantaneous center or use the general velocity method. If you use the general velocity method, you say V of B equals what? Equals V of C plus omega of the object cross R of B with respect to C. You know V of C, I told you it is equal to R times omega. Direction of it is to the right side. That's the condition for rolling without slipping. Omega is clearly negative omega K. And R of B with respect to C is this vector, which is going to be positive R times J. So all you need now is to perform the cross product, K cross J, which is negative I. That's another negative, so it's positive I, and it is R omega. So it's going to be R omega I plus another R omega I. So this is going to be 2 R omega I. So magnitude of it is 2 R omega, and direction of it is to the right side. Okay, so if you want to plot that, show it here, it is going to be like this. For the center, it was R omega. For the top point, is 2 R omega. Okay. Now, can I find that using the instantaneous center? Sure. I say V of B is definitely the distance it has to the center of rotation, which is this point. Remember, this point is what? The instantaneous center. What's the distance it has to the center? Clearly, this distance is what? 2 times R and times omega. Done. Look, I got the same magnitude. Which direction? The direction of it is perpendicular to this R, and the direction of it is determined by omega, so definitely the direction is going to be what? To the right side. So if I want to write it as a vector, it is going to be I, but it is to the right side, and magnitude 2R omega. Correct? So you see, I got the exact same thing without doing any calculation, any projections, any cross product, or anything. And when the mechanisms and the systems get more complicated in 2D, this idea could be relatively faster. Now, sometimes to find those centers, you need to do a little bit of geometry, but in general, remember this method is quite straightforward and it deals with the scalars. Okay, so very easy. Or let's say, for example, if I come back here and say, what's the velocity of, let's say, a point here? If I call a point here, let's say point D, and I say, what's the velocity of D? Well, again, you can find it through saying V of D equal V of C plus omega cross R of D with respect to C, and then you'll find it is going to be R omega I minus R omega J. Or all you can do, if you want, is to connect it to the center. Whatever this R is, multiplied by omega to get velocity of the point, and direction of it is perpendicular to this line. The direction of it is determined by omega. Now, how much is this R? Clearly, you know, it's R and R, so it's R square root 2. And that's what you get. Done. Okay, but if you did it with vectors, you will get R omega I minus R omega J, which gives you the same magnitude and the same direction. So it depends on how you want to deal with it, in terms of I and J or in terms of magnitude and direction. Then this IC method is way easier if you want to do magnitude and direction, not I's and J's components. Now you might say, well, what if the mechanism, what if you have more than one single rigid body here? So if I have more than one rigid body, I have a mechanism like this, how would you do the analysis? And I'll show you that. So here I have this 4-bar linkage, and I say the length of the members are L1, L2, L3, and L4, where L4 is the ground member, the member that does not move. Okay, and these angles, if you want, I can call them theta 1, and maybe this guy, I call it theta 2, and this angle, or this angle, if you want, I call it theta 3. Okay, so if I say at this moment, I give you omega of member 1. So I give you omega 1. I say omega 1 here is given. You give me omega 3 or omega 2. What is omega 2? What is omega 3? And tell me whether they are what? Clockwise or counterclockwise. How can you do that? Okay, so that's the question. I give you all the angles, all the length, and 1 omega, the input omega, and I ask you for the omega of the output and the connecting rod. Right? How can you do that? Well, here, one way, as you know, per what we learned, is we start from the member that you know something about, member AB, and then go to what? Member BC, and then go to CD, and then basically do the analysis. Correct? So that's one way to approach this problem. And find both of the unknown omegas using the relative velocity formula. Correct? Since I know V of A is 0, I know omega, and I know L1 theta 1, I can find V of B perfectly. Through B, I try to find C. And also through D, I try to find C and set them equal, and then through that I can find omega 2 and 3. And you know that based on your dynamics. But here I want to do it through Instantaneous Center. So what I will do is, instead of calling these points A, B, C, and D, right, I would call these points with the corresponding name that they have for the centers. So if you have more than one object, then each object with respect to another object can have a center of rotation. So again, if you have two objects in planar motion, then each object can have a center of rotation with respect to another one. So let me write it for you, and that is called the Kennedy's theorem. Okay, and let me spell it right. It's 2 N's. So Kennedy's theorem says that basically it's not a part of Kennedy's theorem, but it says if you have any two rigid bodies with planar motion, they have a relative instantaneous center. Okay, so first let me write it separate from the Kennedy's theorem, because that's not directly a part of the Kennedy's theorem. So it says any two rigid bodies have an instantaneous center, or you can call it a relative instantaneous center. Now, the Kennedy's theorem says that in planar motion, the instantaneous centers of any three rigid bodies lie on a line. What does it mean? For example, if you have rigid body 1, 2, and 3, then instantaneous center of object 1 and 2, instantaneous center of object 1 and 3, and instantaneous center of objects 2 and 3, they all lie on a line. All these three would lie on the same line, okay? And we use this to help us a lot. Let me show you how that would help us in this problem. So here, first, we find the obvious instantaneous centers between two pairs of objects. So clearly, member 1 is pinned down to member 4. So this point is what? This is the instantaneous center for 1 with respect to 4, because that's where 1 is rotating about 4, and 4, remember, is the ground here. This one is also obvious. This is instantaneous center of member 3 with respect to 4, because 3 is rotating about 4 here. Okay? So that is quite obvious. But if I ask you, where is, for example, instantaneous center of 2 with respect to 4, 2 does not rotate about 4. It's not pure rotation. 2 does rotate and translate at the same time. So the center of 2 with respect to 4 is not somewhere obvious, and we have to find it. But how do we find it? Well, first, here, 2 and 1 are pinned down here, so this is going to be instantaneous center of 1 with respect to 2, or 2 with respect to 1. Because that's where 1 and 2 are pinned, and this is also instantaneous center of what? 2 and 3, because 2 and 3 are pinned down there. Now let's use this theorem. This theorem says if I connect 1, 4 and 1, 2, these 2 points together, on the line that connects 1, 2 and 1, 4 lies what? Lies 2, 4, correct? So on this line, since on this line I have 1, 2 and 1, 4, so IC of 2, 4 should be on this line, correct? Because here I'm talking about object 1, object 2, and object 4, and these 3 instantaneous centers should be on this line. Also here, you see 2, 3, and 3, 4 are here. So it is between objects 2, 3, and 4. So again, 2, 3, 3, 4, and there should be another 2, 4. So if I continue this line also, IC of 2, 4 should also be on this one, because here I'm talking the centers of objects 2, 3, and 4 with respect to each other. So IC of 2, 4 should be on this line and on this line, and clearly it should be what? On the intersection of these 2 lines. So it should be here. And that's where I do what? I would say that is the instantaneous center of 2 with respect to 4. So let me add something here for you. Is on this line, is on this line, based on the Kennedy's theorem. So it is clearly at the intersection of the two lines, and that's where it happens, over there. So if 2 is to be considered rotating about the member number 4, or the ground, it should rotate about this point, which is outside the rigid body. So I can say, instead of member 2 having arbitrary motion, translation, and rotation together, I can say 2 at this moment is doing a pure rotation about the ground, but it is down pivoted here. Okay, so if I want to say that, I have to say member number 2 is temporarily pivoted there. And again, since it's not on the rigid body, I should say what? I should consider it like an extension of the rigid body. So this middle member, instead of considering it to be a bar, I can consider it to be what? Basically a triangular member, right? So I should consider it something like this. And it can be, well, the connecting member should be of any shape, because all that matters is the distance between 2 and 3, right? These 2 pinpoints. The rest of it doesn't matter so much. Okay, so here it is on the hypothetical extension of the rigid body. That's what I want you to know. Fine, so I found these centers, 2 with respect to 4. And now how do I use it? Well, let's say here I have given you omega 1. Now what? Now I need to know this distance from 0.12 to 0.24. So I need to know this distance from here to here. And if I call this distance x, and I call this other distance y, fair? Or if you don't like x and y, I can call them a and b. This is a, this is b. If I know those distances a and b, which I can easily do through geometry, then I say the velocity of this point, whatever it is equal to basically L1 omega 1, correct? So now if I want, I would give them some names now to make it easier for you. So I would call them points A, B, C, D, and E. Now I can say that V of point B is clearly the distance L1 times omega 1. And since L1 and omega 1 are both given, I know V of B. But remember, B also belongs to member BC. And member BC, or member number 2, is rotating about the ground, member 4, about this center at point E. So if I find the distance from B to its own center, which is at E, and I multiply it by omega of this member, which is omega of member number 2, okay, then I can also find velocity of what? Not L2, it is actually A. If I know distance A and multiplied by omega 2, omega of the Conrad, since B is rotating about this point, if I multiply A by the omega 2, unknown omega 2, that would also give me a V of B. And now here A is known, omega 1 is known, L1 is known. Therefore, I can find what? Omega 2. And similarly, now that I know omega 2, I say, what about point C? Velocity of C, since C is rotating about the center at E, it could be written as B times omega 2. And if I know B through geometry, and omega 2 I already found, then I can find V of C completely and now say this is equal to what? C also belongs to member CD, so if I multiply L3 by omega 3, then I can find also velocity of what? C. And guess what? I know L3 omega 2 is given, so from here I can find what? Omega 3. Okay, so pure true scalars without doing any cross product, I am able to find omega 2 and omega 3 without any problem. Now here, let me show you another example, the slider crank mechanism. And here again, I'm going to give some names to the members. So this is L1 and theta 1. The input link. And then this is basically L2. And there is some angle here. Theta 2. And there is this position X of the slider. Or if you want, you can call it 3. Call this member 3, the purple member, the slider. And 4 is going to be the ground. So where are the instantaneous centers here? So clearly, so here I say 4 is ground. And 3 is the slider. If I want to know center of member 1 with respect to ground, that's here. This is IC of member 1 with respect to 4. Here is instantaneous center of 1 with respect to 2. Here is instantaneous center of basically 2 with respect to 3. Because 2 and 3 are pivoted there. So where is 3 with respect to 4 and the rest of it? Especially 3 with respect to 4, if you ever need to find out. Of course, you know 3 is a sliding, pure translation, so its center is at infinity. But here, is there any way I can find any of the other things? So let's say here, I give you omega of the input, I give you omega 1, and I ask you to find velocity of the slider. So how fast the slider is sliding if the crank member in red is rotating with angular velocity omega 1? How can you do that? Well, again, if you give some names to the members, so you can call this point A, you can call this point B, and this point C, and then go from A to B and B to C and trying to find the omega of member BC as well as V of point C or V of point 3, V of object 3 basically here through general velocities. But another way is through instantaneous centers. And the one that specifically I am interested at this point is so you see here, that's member 2. If I can find 2 with respect to 4, 2 with respect to the ground, that makes my life a lot easier, because then I can say instead of 2 having general motion, the conrod, it can have a pure rotation about a instantaneously fixed point. So here I am interested in IC of 2 with respect to 4. 4 is the ground, so it's always important that you find your ICs of any point with respect to the ground. So where is 2 with respect to 4? Which clearly should be outside the rigid body, BC, but where? So here I have 1, 2, and 1, 4. So if I continue this line, then IC of 2, 4 should be on this line. based on the Kennedy's theorem. Also, that's 2, 4. I need another line that defines 2, 4. So here I have 2, 3. If I knew 3 with respect to 4 somewhere, then on the line connecting 2 to 3 and 3 to 4 would be 2 to 4. But where is 3 to 4? 3 is the sliding object and 4 is the ground. Okay, so if you want, I can connect these together and call this whole thing 4. Number 4. So 3 with respect to 4, you know, when you have pure translation, the center is at infinity. In which direction? Perpendicular to the direction of VC. So I draw a perpendicular to the direction of VC. And on this line is what? This is IC of 3 with respect to 4 at what? At infinity. It is on this line, but at infinity. So now I have 2 to 3 and 3 to 4. So now on this line, on this vertical dash line that connects 2 to 3 and 2, 3 and 3, 4 should also lie what? Yes, 2 with respect to 4. So IC of 2, 4 should be on this line also. So if I continue them where they hit each other, that is going to be what? That is going to be the instantaneous center of 2 with respect to 4. And here, let me try to move this a little bit further down for you so I can add something to it. This guy allows me to move it. Didn't. So here I try to go off a little bit. And so here I say instantaneous of 3 to 4 is on this line, but at infinity. Okay, so this point here is what? This point here is the instantaneous center of 2 with respect to 4. So now if I call this length again from here to here A, and I call this length from here to here B, then I can find what I need. Okay, and let me try to make this a little bit cleaner for you because it's just too hectic, too many things on it at the same time. So IC of 2, 4 should be on this line. Okay, now it's a little better. And so now I can say, and I can call this point anything that you want. I can call it, for example, E, doesn't matter, or D. Now I can say that velocity of point B is clearly equal to L1 omega 1, and both of them are given. But B, which is on member 2, also rotates about pivot point E. So if I multiply the distance from B to E, which is A, times omega of the member, which is omega 2, that should also give me V of B. If I can find A through geometry, which I'll show you, then omega 2 can be found from here. And now point C, which is what I care about, correct? V of 3 or V of C, if you want to call it. Let me call it V of C. Then we have C, since C belongs to member 2, 3, and is rotating about E, if I find the distance of C to E, which is B, multiplied by the same omega 2, then that will give me what? We have C, correct? And remember, B I can find through geometry. Omega 2 I already found, and I can find what? Velocity of the slider. So you see, using Kennedy's theorem, using instantaneous center and some geometry, because we need to find these distances A and B, and I'll show you, then you can easily find what? You can easily find the unknowns of your kinematics problems. Now, a few things here, and then we'll talk about these two problems again, but this time with numerical values. So I'll redo these two problems for you, both the slider crank and the 4-bar linkage, and I will do through numbers, and I will calculate those distances A and B through what? Through geometry, so you exactly know what I'm talking about. So this lecture is complete, but there are other centers if you want to find in the case of a slider crank or in the case of 4-bar linkage, but they are not necessarily useful. I mean, not that you cannot use them, but you don't really you can use them, but they are not easy to use. So what do I mean by that? So here, let's say this is my 4-bar linkage again. Right, and I have 4 pivot points, and they were L1, L2, L3, and L4. Now, if I name them, this one was IC of member 1 with respect to 4, right? The crank with respect to the ground. This one was IC of 3 with respect to 4. This one was IC of 1 with respect to 2 or 2 with respect to 1. They are the same thing, okay, whether it's a 2, 1 or 1, 2. And this is the IC of 2 with respect to 3 or 3 with respect to 2. Now, if you remember, I connected 1, 4 and 1, 2 together and continued the line, and I said 1, 2 is on that line because, 2, 4 is on that line because 1, 2 and 1, 4 are. Right? Basically, they both have 1. The numbers they don't have is 2 and 4. So IC of 2, 4 should be on that. Also, if you look at these again, they both share 3. They don't have, one of them has 2, one of them has 4. So 2, 4 should be on this line as well if you connect. So if you connect, that point is the instantaneous center of 2 with respect to 4. That's the hypothetical point on the member 2 that you can say member 2 is rotating about it with respect to the ground. But there are other ones, again, as I said. For example, here, if you connect these two, you see 1, 2 and 2, 3. What they don't share between 1, 2 and 2, 3 is what? You see, they both share 2. So if you connect these two now, they have 1 and 3. So if you connect this line, 1, 3 should be on that. Also, these two the same. They share 4. They don't share 1 and 3. So 1, 3 should be on this line as well. So here is IC of 1 with respect to 3 or 3 with respect to 1. Okay. And how many are they? There are 6 of them. And in general, if your mechanism, based on the Kennedy's theorem, where is that? Let me add it to the Kennedy's theorem for you. So here, you see, it says every 3 of them are in the on the same line. Now, if your mechanism, your system, has n rigid bodies. And I mean including ground. So including the ground, okay, ground is included here. If you have n rigid bodies in your system, then there are n times n minus 1 divided by 2 instantaneous centers. That you can find. So if I go back to this example here, I have 4 members, so n here is 4. So the number of ICs is equal to what? N times n minus 1. So it's 4 times 3 divided by 2. So I should have 6 ICs. Do you have 6 ICs? Yes. If you see here, 1, 2, 3, 4, 5, and 6. Now, clearly this one is very useful because here, out of these 2 members, 2 and 4, one of them is a fixed member. One of them is 4, which is omega of 0. It's 2 that is rotating. So when I find omega of this Conrad, as I did here for you, when here I found the omega of Conrad through this formula, correct, here and here, because B and C were rotating about point E, and E was center of 2 with respect to 4. So you see the omega I used was what? Omega 2. Or you can say omega of 2 with respect to 4 if you want. But remember, 4 does not what? Does not rotate. So omega of 2 with respect to 4 is the same as what? Omega 2. Okay, no problem. But here, if I want to use this point, this is 1 with respect to 3. So the omega that I have to use is omega of object 1 with respect to object 3. But 3, the reference for 1, or 1, the reference for 3, they are both rotating. So if I, let's say, find this distance from here to here, I call this distance C, then I can say velocity of this point, whatever this point is, let's call this point A. Velocity of point A equals L1 omega 1, where this is omega 1, right? I can say that. And I say, well, A is rotating about this point, so I can multiply that distance C, but by which omega? Since this is omega of 3 with respect to 1, I have to say omega of 1, 3. And omega 1, 3 is omega 1 minus omega 3. And that's fine. Through here, you can find omega 3 probably, right? If you know distance C. But remember that here your reference is what? Omega 1 with respect to 3, not 4. If it's 4, then omega of 4 is 0, life is good. If it's not, then it's the relative omega of the 2 members, which is the difference between the omegas. Okay, so you have to know that if you're using anything where one of the pairs is not ground, you have to pay attention to the omega that you're using. The same thing can be said about this slider crank, right? So if I have this slider crank, again, here is L1, this is L2, this is member 3, this is member 4. And again, there are 6 instantaneous centers. because n is 4 here again. But where are they? So here, this is I of 1 with respect to 4, or IC of 1 with respect to 4. This is 1 with respect to 2. This is 2 with respect to 3. Now, 3 is a sliding with respect to 4. So if you remember, since we have point 3 is horizontal, the instantaneous center is perpendicular to that direction of motion at infinity. So IC of 3 with respect to 4 is at infinity. Okay. So now, could you give me the other two instantaneous centers? Yes. If you remember, last time we found one of them. And we said that, well, these two share 1. They don't share 2 and 4. So IC 2 and 4 should be on that line connecting them. Also, these two share 3. They don't share 2 and 4. So 2, 4 should be also on that line. So the intersection here, which is not at infinity, but it is at a finite distance, this is IC of 2, 4. Okay, let me get some distance here. And move this guy up. So this point here is IC of 2 with respect to 4. Now here there is 1, that is 1 with respect to 3. Do you have 1 with respect to 3? No, we have to find it. And how can I find 1 with respect to 3? Well, if this time I connect these two, 1, 2, and 2, 3, since they both share 2 and they don't share 1 and 3, so 1, 3 should be on this line. 1, 3 should be on that line. Also, is there any other sets that I can use and find 1 and 3? Yes. Which set? So I did 1, 2, and 2, 3, so I'm good. Now, you see here, if I could connect this 1, 4 to 3, 4, they share 4, they don't share 1, 3 again. But 3, 4 is at infinity and it's up. So what I can do is to draw a line here as well, all the way to infinity, and say, well, IC of 3, 4 is here at infinity, correct? When it's at infinity, this small displacement of L4 doesn't matter, so you can say it's here or here. And so this intersection now is what? IC of 1 with respect to 3, because again, these two share 4, but they don't share 1 and 3. These two share 2, they don't share 1 and 3, so 1 and 3 is over there. Okay, so if you want. But again, remember, 1 and 3, they you have to be careful about them, especially 3 that does not have any omega. Okay, so I would always try to use the ICs that one of the two pairs is the ground and not use this one. But again, you can always find all of them and use them if you use proper omega. And there is one way to make sure that you can find all of the ICs, and that is the circle method. So what this method does is it basically puts the numbers, a bunch of numbers for each one of the rigid bodies on a circle. So you have member 1, member 2, member 3, and member 4. and then try to see which one you need to find. So in the beginning, if you remember, I had 1 4 1 2 2 3 1 4 1 2, so I could connect 1 4 and 1 2, and then I also had 2 3, correct, and I also had 3 4, so I had these guys. And so now what I need is basically, let's say 2 to 4. How do I find this? Well, if I want to go from 2 to 4, one way is to go connect 2 to 1 and 1 to 4 together. Or I can connect 2 to 3 and then what? 3 to 4 together. That's two different ways that I can go from 2 to 4. So I connect 2 to 1, 1 to 4, which is this one. 2 to 1 and 1 to 4, I connect them. And then what? The other way is 2 to 3, 3 to 4. And this is 2 to 3, 3 to 4 is at infinity. So I connect them, and then wherever they intersect, that's 2 to 4. And the same thing for the other one. If I want to go from 1 to 3, one way is to go 1 to 4, 4 to 3. This is 1 to 4, 4 to 3, which is this line. And the other one is to go what? 1 to 2 and again 2 to 3. And that is 1 to 2. Where is that? 1 to 2 and 2 to 3, which is this one. And that is going to be 1 to 3. Okay, so this method of marking one point on a circle for each one of the rigid bodies, the ones you find, you connect them. It's like a graph, basically. And the ones you don't, you try to find it through two alternative paths. And those paths, each one define a line. You intersect the lines with each other, and that will give you the intersection, the location of the missing instantaneous center. Okay, that's called the circular method for finding all of the n times n minus 1 divided by 2, or combination of 2 out of n centers of rotation. So far I talked about the importance of instantaneous center of rotation and how to find it in a couple of different mechanisms, and the Kennedy's theorem, and how many of them exist, how to find them, and so on. And now in the next couple of examples, I show you how to find these distances AB, or here this other distance that I have AB, through geometry with numerical numbers, and I provide you some further guidance in general on finding the location of instantaneous center of rotation for any rigid body. Okay, here to provide you with numerical examples, consider this 4-bar linkage ABCD, and omega of the input AB is 10 radians per second counterclockwise. You want to find omega 2 of member BC and omega 3 of member CD. Okay, so here, if we go with the same notation that we did, and we call these members basically member 1, member 2, member 3, and member 4 to be the ground, then we can annotate the ICs to be IC of basically 1, 4 here, and then this is going to be IC of 3 and 4, and this is going to be IC of 2, 3, and this is going to be IC of 1 and 2. And if you use Kennedy's theorem, connect the line of 1, 4 to 1, 2, and continue that, you know this is going to go to completely upright direction, and I of 2, 4 is going to be on this line. Also, if you connect IC of 2, 3 to 3, 4, again 2, 4 is going to be on that line. So if we continue this line and the other line, the intersection point is going to be the center of rotation for member 2 with respect to member 4. So this is IC of 2 and 4. And now here, velocity of point B is going to be, since B belongs to member AB or member 1, and 1 rotates with respect to 4 with angular velocity omega 1 of 10 radians per second, the distance between B to the center for that member with respect to 4 IC14 is 2 meters. So it is going to be 2 times 10, correct? R times omega, correct? If you want, let me write it like this. It is going to be the distance from B to IC of member 1, 2 times omega of 1. And clearly this number is equal to 2 times 10. So it is going to be 20 meters per second. And because of the direction of omega 1, which is counterclockwise, V of B is of course going to be to the left. Now B also belongs to part number 2, and 2 with respect to 4, which is ground, also rotates with some angular velocity omega 2 or omega 24, you might want to call it. But remember that omega of 4 is 0 in this case. So I can also say this V of B that I just found is also equal to this V of B. It is also equal to the distance from B to the IC of 2, 4. Okay, and this is, by the way, 1, 4, not 1, 2. 1, 4. Okay, times omega of 2. And again, I can write this omega 1, 4. I can write it omega 2, 4. Okay, so if you want, I can say this is omega 1, 4, and I can say this is omega 2, 4. But this is omega 1 minus omega 4. And remember, omega 4 is 0, so it's the same as omega 1. The same thing here. This is omega 2 minus omega 4. And since omega 4 is 0, this is omega 2. So omega 2, I don't know. The distance now I need is this distance from here to here. And you might call it whatever you want. Let me call it x. So I need this x. Also, later I need this distance from here to here, y. And how do I find them? In this case, because line BC is parallel to line AD, I have 2 triangles. If I call this center here point E, if you look, I have 2 triangles, EBC and EAD. So I can say that triangle EBC is similar to triangle EAD. Both have 1 common angle and both have a 90-degree angle. Since they are similar, the ratio of the sides are equal. So I can say that EB to EA is the same as EC to ED. And that is the same as BC to AD. Okay, and now the numbers for them, BC is 2, AD is 4. So this ratio should be half for all of them. EC is X and Y. So EC is Y, the other one is X. EA is sum of EB and BA, so it's X plus 2. And this guy is Y plus the length of member CD. And the length of member CD, since you can see here, this is 2 and this is 2. So the length of this member is a square root 2 times 2, correct? 2 square root 2 or square root of 8. Because it's 2 squared plus 2 squared, the square root of that. 2 square root 2. So from here, clearly, if you solve, your x is going to be 2 and your y is going to be 2 square root 2 meters. And so here, the distance from B to E is distance x, which was 2. So this is 2 times omega 2. And 2 times omega 2 should be the same as 2NE. From these two, you clearly can see that omega 2 is 10 radians per second. So that's one of your omegas. Omega of this member, BC, is 10. Now, which direction is it? Clockwise or counterclockwise? Consider that B is rotating about this pivot point, hypothetical, okay? It's not an actual pivot point, it's just a hypothetical pivot point. B is rotating about that with omega 2. And V of B is to the left. So the only option for that to happen is omega of 2 should be what? Definitely it should be clockwise for V of B to be to the left. So clearly this is what? This is clockwise. Okay, so I found omega 2 and I found the direction of it. Now I can use a similar thing. This time I focus on point C. I say V of C, since C belongs to member 2 and 2 rotates about pivot point E. So if I multiply the distance from C to the instantaneous center 2, 4, which we call it Y, times omega of member 2, that should be V of C. And this distance, we called it Y, that is 2 square root 2, and omega of that member is 10. So velocity of C is going to be 20 square root 2 meters per second. But remember, C also belongs to member CD. And this member CD, or member 3, is rotating about pivot point 3, 4. So if I multiply the distance between C to center 3, 4 and multiply it by omega of that member 3, okay, that should give me the same number. Now again, this distance is also 2 square root 2 and times omega 3, correct? And clearly again, from these two, you can see that omega 3 also has to be 10 radians per second. Okay, so the answer to omega 3 is also 10 radians per second. Now, which direction? So if we go back here, since omega 2 is like that, clockwise, and C is rotating about point E, so V of C should be what? Perpendicular to the line connecting C to E. Okay, so if I consider this line connecting E to C, V of C is perpendicular to that, so V of C is going to be like that. And also, since C is rotating about D and velocity is to the left and downward, the only option for omega 3 is to be what? Counterclockwise, like this. So clearly this is going to be what? Counterclockwise. Okay, so I found both of the unknown omegas and their direction. I did not use any vector notation or anything. And I did it with instantaneous center. I had to find distances x and y through what? Definitely through geometry. That's the only way to go about it. And it will be a little bit more difficult when the member here, member BC, is not horizontal. When it's not horizontal, then you're not going to get these similar triangles, and you have to use the laws of sine and cosine to find distances x and y. But in general, there is always a geometry trigonometry solution to find these unknown distances. And that's why some students do not like the instantaneous center method, because they would rather do the cross products and calculate with vectors than to find these distances. So it depends on whether you prefer vectors and cross product or you prefer doing geometry, okay? But there are two different approaches to that problem. And now, just to make the topic complete, remember that we had one more center here, So here we have found 5 of the centers: 2, 4, 1, 2, 1, 4, 3, 4, and 2, 3. There is one left, and that is 1, 3, correct? 1 with respect to 3. Where was that? If you remember, we had to connect 1, 2 to 2, 3. So it is on the line connecting B to C. And then 1, 4 to 3, 4. So we have to connect A to D. But the problem is, if we continue these two lines, B, C, and AD, they do not intersect. So your omega, center of rotation of 1 with respect to 3 is going to be at infinity, because these two parallel lines would not intersect, okay? But just wanted you to know about it. So this is one of the examples I wanted to do for you numerically using the center of rotation. Let's look at one more. Okay, so the next problem is a slider crank mechanism, and the length of each member is 2 meters. The angle of one is 45. Clearly, the angle of the other one with respect to the x-axis here is also 45 degrees. Omega of the input AB is given as 2 radians per second clockwise. You want to find omega of the conrod BC as well as the velocity of the slider or piston. So again, I would do it through the instantaneous center method, and again, I call these members with some numbers. So this is member number 1, this is member number 2, 3 is going to be the slider, and 4 is going to be the ground. And I try to locate the instantaneous center. So this is clearly member 1 with respect to 4. Okay, so this is IC of 1 and 4. Then this is IC of 1 and 2. This one is IC of 2 and 3. Now, if you remember, 3 is sliding horizontally and no rotation, so the center is at infinity, and the direction of the line connecting member 3 to its instantaneous center with respect to 4, 3, 4 is perpendicular to the direction of velocity of VC, since VC is horizontal. So what we need is to draw a vertical line to the motion horizontal. And so if I can continue this a little bit. So the IC of 3 with respect to 4 is at infinity. Now, we need 2 other ICs. One of them is 1 with respect to 2, and the more important one is 2 with respect to 4. So if I connect 1, 2 to 1, 4, 2, 4 is going to be on this line. And then if I connect 2, 3 to 3, 4, again, 2, 4 is going to be on this line. So wherever these two intersect here, I say this is a temporary pinpoint. Remember, it's not a permanent pinpoint. And this is going to be IC of basically 2 with respect to 4. And this is enough to give me the 2 answers I'm looking for. All I need to do is to say, and I can give this point a name too. I can call it E or D if you want. I say velocity of point B, since B belongs to AB or member 1, I can find it by the distance from point B to the instantaneous center of 1, 4 times omega 1, 4. But remember, omega 1, 4 is omega 1 minus 4, and omega 4 is 0. So it's simply omega 1. And this distance is 2 meters. So it is going to be 2, and the omega is 0.2. So it is going to be 0.4 meters per second. And clearly, because of this clockwise rotation, V of point B is perpendicular to that. So here this angle is 45, this angle is 45, so this angle is 90 degrees. And so it is going to be a line member BC. So along this line is going to be V of B, because it has to be perpendicular to the radial line. Okay, so that's about V of point B. But B also belongs to member BC or member 2, and member 2 is rotating, any point on member 2 is rotating about IC24. So I can also find this by multiplying the distance from B to D, or B to instantaneous center of 24, times omega 24. And remember, omega 24 is the same as omega 2. The only thing is this distance now. I have to find this distance from here to here, and I can call that x. And again, I need this distance from here to here, and I need to call that y. And I need to find distances x and y. And again, I can use similar triangles. All I need is to consider if I connect B or draw a perpendicular from B to CD like this, and call the intersection point E. Then I have triangle BDE and triangle DCA. So BDE is similar to DAC. And again, that means the ratios have to be equal. So it means BD over AD has to be the same as DE over DC, and the same as BE over AC. And the numbers here are what? So BD. So here we have to find the distances. So here I have a 2, a 45, a 2, a 45. So this distance from here to here is going to be basically, if you draw a perpendicular here, each portion of it is 2 cosine 45. That's another 2 cosine 45. So it is going to be 4 cosine 45. Okay. And 2 cosine 45 is the distance from B to E, but A to C is twice as much, and it is 4 cosine 45. So if you want to go there and write it down, this distance is 2 cosine 45. This distance is 4 cosine 45. So the ratio is 1/2. Now, AB, BD. BD I don't know, that's x. AD is x plus 2. DE I don't know, that's called y. And this one is DE plus EC, which is y plus. Now, EC is clearly the vertical distance, and that is 2 sine 45. Okay. So clearly all the ratios are half, and that means I can find my distances, x and y, by solving through equality of the two ratios. Excuse me. So here it means x has to be 2 and y has to be 2 sine 45, and this is a square root 2 over 2, so it should be just a square root 2 meters. So that's x and y. Now this distance B to IC is clearly x, and x is 2. So 2 omega 2 is now equal to 0.4, so it means omega 2 has to be 0.2 radians per second. I found one of them, one of the unknowns, because this is the same as omega BC, correct? This guy is the same as omega BC, because BC is 2. So I found one of them. Which direction? Clearly, if B is to rotate about D and the velocity of B is downward to the right, the only solution for it is for this omega of BC or omega of 2 to be this way. correct? That's the only solution. And it has to be counterclockwise. Now, what about velocity of the slider? So clearly velocity of the slider, since slider here is on object 2, 3, or point C, belongs to member 2, basically, object BC. So I can say it is rotating also about D. So if I multiply the distance from C to the instantaneous center, 3, 4, and multiplied by, 2, 4, and multiplied by omega 2, or omega 2, 4, which is the same as omega 2, this distance is y plus EC, which is this distance here. And that distance is 4 sine 45, which is 2 square root 2. That is going to be omega 2. And omega 2 is already calculated as 0.2. So you're going to get 0.4 square root 2 meters per second. And clearly, because omega 2 is counterclockwise, V of C has only one option, and the option is to be to the right side. Okay, so I found both of these simply through instantaneous center of rotation. Again, for distances x and y, life was easy because I could use similar triangles. Not always it is that easy, okay? And I'll show you an example, but remember, in general, not always you get these horizontal lines and similar triangles. Okay, now here, remember, we have one more center of rotation that we did not find, correct? And that is it is 1 with respect to 3, correct? Where is 1 with respect to 3? So remember, we had to continue this, and it was somewhere here, but omega of that is omega 1, 3, which is omega 1 minus omega 3, and remember, 3 does not rotate, so can I use that to do anything? Well, let's do that. So remember here, if I draw a perpendicular from this point all the way up, and that keeps going to infinity, because that's where I C of 3, 4 is. Now here, if I connect 3, 4 and 1, 4 together, which is this line, 3, 4 is going to be on, 1, 3 is going to be on that. Also, if I connect 2, 3 to 1, 2, again, 1, 3 is going to be on that. So if I continue the line of BC to the vertical line drawn from A, this point here is what? This point is the instantaneous center of 1 with respect to 3. And you can call this point also something. Maybe you can call it F. Now the question is this. Can I also find velocity of C through the distance of C to this center? So can I say that velocity of C is equal to the distance it has to the center, which is point C to F, basically, correct? Distance CF. Or if you want, you can write it as C to instantaneous center of 1, 3, which is F, times omega 1, 3. And omega 1, 3 is omega 1 minus omega 3. But remember 3, object 3 is the slider, which does not rotate. So I can write this as 0, and this was 0.2. So what is this distance here from C to IC? So I need to find for that the length from B to F. If I find B to F, add it to BC and I'm good. But how do I find that? Again, here I need similar triangles. Again, I need to draw a perpendicular from B to AF and then look at the triangle. Let's call this G, for example, BFG and FAC, and say again they are similar. And again, this is 2 cosine 45, this is 4 cosine 45, so all the ratios are half. Therefore, FB is the same as BC, so it has to be 2 meters. And this distance also has to be 2 sine 45, 2 sine 45. So that distance has to be 2 meters. And so the distance from C to F is 4 meters. So I can say this distance is 4 meters. And I multiply 4 times 0.2 and I get 0.8. Now, if you compare these two to each other, clearly you see the numbers are not the same, right? Clearly, you see the numbers are not the same. And we can check everything here for you, but if you check and go back and look at all the numbers, you see all the calculations are correct, right? So as you can see, clearly these two numbers do not match, and as I said, when you go and check all of your calculations, they're all correct. So the moral lesson is this: you cannot simply use such a thing. Okay, this thing here is not correct. Okay, this is not going to work. When you use an instantaneous center and you find the distance from a point on the rigid body to its this instantaneous center and multiply it by omega of that rigid body to find velocity of the point, where you define omega of that rigid body, it has to be with respect to an inertial frame or an stationary object. Since here object 4 is stationary, only the centers that are for each one of the parts with respect to what? 4 can be used to apply this formula. So 1, 4 and 2, 4 are good. 3, 4 as infinity is not going to give you anything because the distances are infinite. But those two are good. But 1, 3, since the reference of 1 is not 4, is 3, which itself is moving and it's not stationary, I'm not able to use this formula. Okay, so this formula is wrong. This is not going to go anyway, so I'm not going to use this. I only use the one where the distance from the point to the instantaneous center of that member with respect to the ground is used. Okay, so that's a very, very important thing that can easily make you lose your credit because you think it's a very shortcut and fast way to solve the problem, but that is not the case. Okay, so I mentioned that. Finally, as I said, I want to talk about different scenarios for locating the instantaneous center. So there are several scenarios for instantaneous center. Scenario 1 is this: you basically know V of one point on the rigid body as well as omega of the rigid body. So if I give you this rigid body and I say omega of the rigid body is so much, and I say the velocity of one point on the rigid body is also perfectly known. So I say velocity of point A, I know its magnitude, I know its direction. Okay, so I know this angle, for example, or I know this angle. Right? If I say that, can you find the instantaneous center for this rigid body? Yes. You know that velocity of any point is always equal to its distance from the instantaneous center times omega. So the radial distance from point A to the center R is clearly equal to magnitude of its speed divided by omega of the rigid body. Also, velocity of this point should be perpendicular to that radial line. So if from this point I draw a perpendicular line to velocity of A, and then from this point A, I separate using a compass. I choose a distance of R. So let's say R is this much. So it has to either fall on this side or this side, okay? Where this is R and this is R. So one of these 2 points is the center. Which one? It comes from omega and V. If you look at the direction of V and omega, which is counterclockwise, clearly this point has to be the center. If it's this point and you rotate with that omega, V of A is going to be downward. Okay, so we choose this one. This is your instantaneous center. So case 1, VA as a vector is known, and omega as a vector is known, magnitude and direction. That's scenario 1. You can find the center. Scenario 2. Scenario 2 is you have the rigid body, you don't know omega, and you don't know magnitude and velocity of magnitude and direction of velocity for 2 points, but you know their line of action. So for example, you know that this point has to move either this way or the opposite way. So I know this point moves like that, and I know, for example, this point moves like this. How fast? I don't know. Which direction exactly? I don't know. I just know these lines of actions for VA and VB. Then again, you draw perpendiculars from VA and VB at points A and B. Okay, so if this is point A, you draw a perpendicular to VA at A, and you draw a perpendicular to VB at B. Wherever they intersect, that's again what? The instantaneous center. And this is the case which you see in most of your examples. This is the case that you see in most of the examples. Remember the wall problem I mentioned earlier? Correct? So you have this wall, and you have some ladder or some object that is sliding on the wall because there is no friction. So if you remember here, this point, the only option it has in order to keep the contact with the wall is to either go what? Up or down. That's the only way this point can move. And this point here on the floor can only go what? Left or right. It can only move horizontally. So if I draw a perpendicular to these two velocities, this is 1 and this is 1. Wherever they intersect, this is what? The instantaneous center. And as I said, this instantaneous center is outside the rigid body in this case. Sometimes it is inside, sometimes it is on the hypothetical extension of the rigid body. So this is most of the cases. So all I know is lines of action for VA and VB are known. I don't know the speed of them. I don't know exactly which direction. I just know the line of action. This is most of the time the case for finding the instantaneous center. And finally, the last scenario that you will see is very similar to scenario 2, but the fact is these two lines of actions for VA and VB, they are parallel. If V of 2 points on the rigid body are parallel, then if you draw two perpendiculars at those 2 points to those two velocities, they are not going to intersect at a single point. Okay, so where is the instantaneous center? So one example is, let's say here is a rigid body, and you have 1 point here moving this direction, and you have 1 point here moving to that direction. So this is VA and this is VB. In this case, that these two are parallel, not only you need to know that their line of actions that are parallel, but that's not enough. You also need to know the magnitudes of VA and VB. In other words, you need to know perfectly VA and VB. So here, VA and VB as a vector, both magnitude and direction, are known, but VA and VB are what? They are parallel. Where's the center? So there are two scenarios here. Either VA and VB have the same direction or opposite directions. If it's opposite like this, what you need to do is you connect points A and B together like this. Also, from the end of VB and end of VA, if they are drawn to the scale, they have to be drawn to the scale. So if this is 2 meters, that is 4 meters per second, this has to be twice as big as the other one. So they have to be drawn to the scale. Then you connect end of VA to end of VB, and the intersection here is going to be the center. So here, VA and VB, they are parallel but opposite directions. The other scenario is they are parallel, but they have the same direction. Okay, so for example, VA is like this and VB is like that. Or let me put A as the bottom point. So now they are parallel. Now what? The same technique that you did in the previous time. Again, you connect A and B and continue. And then again, if A and B are drawn to the scale, again, can continue from end of VA to end of VB and extend. And again, wherever they intersect, that's the center. Okay? And you can easily show why that's the case. And then you might wonder, well, what if both points are parallel, the same direction and the same magnitude? Now what? So if I have this case where I have 2 points and their velocities are parallel and the same magnitude, now what? Now if you connect them together and connect the end of velocities together, they would never intersect, and of course they don't. Here the instantaneous center is at what? At infinity. Why? Because if velocity of 2 points on the rigid body are equal, correct? So if VA equals VB, or any arbitrary 2 points, they have the same velocity, it means the object is doing what? Pure translation. That's the definition of pure translation, which means omega is what? 0, or the instantaneous center is at what? At infinity. Correct? And of course, that's the case. So these are different ways to determine the instantaneous center. And I mentioned a bunch of examples. I mentioned Kennedy theorem and everything. Now, before I finish this topic, I would like to give you an example of a case of, let's say, this, maybe the 4-bar linkage, where this middle member BC is not horizontal like this. It has angle. How do you find distances A and B? I just want to make sure you know the laws of sines and cosines. So let's say I have this 4-bar linkage, correct? And the length of these members are given. So L1 is given, L2 is given, L3 is given. Then also, let's say here, This angle theta 1 is given, angle theta 2 is given, and this angle theta 3 is given. All of them are given. Clearly, you can also find this distance L4 because it is going to be a function of L1, L2, L3, and their thetas. So these are known. And as I said, the instantaneous center of the middle member with respect to the ground is where you continue these two members, and that's here. And you wanted to find these length, A and B. Now, everything else is given to you. All angles, all length, everything is given. You just need to find A and B. And so if you focus on this triangle, one side of it is L2. And if you look at this angle here, this angle here is not hard to find, right? Because this whole angle here from this horizontal line to the extension of this member is theta 1. This small portion is theta 2. So clearly this angle is what? Theta 1 minus theta 2, correct? And is there any other angle that I can find? Sure. What is this angle, for example? Well, if you look at the big triangle, you have theta 1, theta 3. So this angle here is going to be pi minus theta 1 minus theta 3, right? Sum of the three angles should be 180. So I know two of the angles, and definitely I know the third angle, correct? So this is clearly going to be sum of this one plus this one plus this one is 180. So if I add them together, how much is that angle? Clearly, I have to subtract pi minus the summation of these two. So it is going to be theta 1 plus 3 minus theta 1 plus 2. So there's going to be theta 3 minus theta, or theta 3 plus theta 2. Correct? Now, if you add them together, the theta 1s cancel, theta 3s cancel, theta 2 pi. Yes. So now here I have all of these angles. Good. And now it's not hard to do the law of sine or cosine. So if I use the laws of sine, which is in this case easier, it says length A to the sine of angle in front of it, which is theta 2 plus theta 3, which I know, equals B over sine of angle in front of it, which is theta 1 minus theta 2. That is equal to this member, which is L2, over sine of angle in front of it, which is pi minus theta 1 minus theta 3. And since all of the angles are known and L2 is known, from here I can find what? I can find both A and B. Okay, so that's the way to go about it in case this member, middle member, is not horizontal, and it happens most of the time, of course. It's very exceptional that this member is horizontal at the moment you're talking about. Even if at this moment is horizontal, at the next time point it is going to move and not be horizontal. Unless members L1 and L3 are what? The same length, so it becomes a parallelogram, and then member L2 is always going to stay horizontal, which is an exceptional case of four-bar linkage. But other than that, this member would change angle, and you have to use the laws of sine for it. So hopefully I could cover this important topic, and I'll see you in the next lecture.